Welcome to the Unit 1 Section 2 video on compound inequalities. Before we get into talking about compound inequalities, let's review first how we can express and solve simple inequalities. So first, how do we express solutions to a simple inequality? Well, we have three ways. The first of which is set notation. And the big giveaway that we're using set notation is the set of curly braces that you see in the solution. Okay, so the curly braces represent a set. And we're going to just simply put in whatever our solution is into those curly braces, preceded by the variable and a vertical line. Now that vertical line represents such that. That's mathematical shorthand for the phrase such that. So the way this would read is the set of all x such that x is less than or equal to 6. Our second way of notating an answer is through the use of a number line. And I like number lines because they're very visual. It's very easy to see what's included. So for x is less than or equal to 6, we are going to fill in the 6 because it's included as indicated by the equals to. And then we're going to shade to the left because we want all values that are less than 6 for our variable x. So that would include 5, 4, 3, 2, 1, 0, all the way down to negative infinity. Remember, if you have the equals part on your inequality, then you're going to use a closed dot because we're including it. If we do not have the equals part, then we're going to use an open dot because we're not including that value. And then finally, we have interval notation. And in interval notation, we have our lower and upper bound. And we indicate whether we include it or not by using either a parentheses, meaning that we do not include the value, which is the case with any infinity, or less than or greater than signs with no equals to portions. Or we use a bracket, which is indicated by this bracket on the 6, meaning that we are including it as part of our solution set. Okay, so those are the three ways that we are going to represent solutions. When it comes to solving a simple inequality, well, there are just a few things that you have to keep in mind. One, you want to, where possible, combine like terms first. So if you have two x's on one side, go ahead and combine those. Okay? Then you want to isolate the variable, very much how we do with an equation. We want to isolate the variable to one side of the inequality. Now, this is a key to remember. Remember to reverse the sign of the inequality if you multiply or you divide each side by a negative. Okay? So let's look at this first example where we can use some of these rules. Our first example is negative 6x plus 10 is less than negative 2. Well, the first thing we're going to do is subtract 10 from each side. And that gives us negative 12 on the right-hand side. Then we're going to divide by negative 6. And when we do, we have to flip the inequality because we divided by a negative number. So that gives us x is greater than 2 as our solution. So now that we have our solution, let's represent it in set notation. We simply take that solution we just found and drop it into the context of a set notation. So the set of all x such that x is greater than 2. Then on the number line, we are not including the 2, so we are going to put an open dot on the 2, and then we are going to shade to the right because we are including all values that are greater than 2. And then in interval notation, our 2 is our lower bound, and we are not including it, so we use a parentheses, and then our upper bound is going to be infinity. And again, any infinity, we do not include that as well. Okay, let's move on to the second example. We're going to solve negative 7 plus 3x is greater than or equal to 3 plus 8x. Okay, so we have a couple of different options. Let's first subtract 3x from each side. And that's going to give us 3 plus 5x on the right-hand side. Now we can subtract 3 from each side. And you notice that the sign does not flip when you subtract a negative. Okay? You only flip the sign when you divide or multiply it by something that's negative. Even though we're subtracting by 3, subtracting and adding, the sign's going to stay the same. And then finally, dividing each side by 5, you'll notice that's a positive 5 we're dividing by. So again, the sign's going to stay as it is. And so our solution is -2 is greater than or equal to x. When we write this in set notation, we often like to lead with our variables. So I'm just going to flip the whole inequality around. Start with x, have our inequality sign still point to x like it did up here, and then we have -2. So the solution would read as x such that x is less than or equal to -2. So -2 is our point of interest. Since it's less than or equal to, we're going to fill it in because we're including it. And then since all our values of x are less than, we're going to fill to the left. And then finally, in interval notation, once you have your number line, it's very easy to do interval notation. Our lower bound is going to be -infinity. Our upper bound is going to be -2, and we're including that -2 as part of our solution. All right, now that we've worked a little bit with simple inequalities and we've kind of gotten ourselves primed, now let's start talking about compound inequalities. And before we get into solving them, let's just talk about how we're going to express the solutions that we get in the end. We'll add solving here in just a little bit. So, a compound inequality, first of all, let's get what a compound inequality is. A compound inequality is a sentence with two simple inequality statements joined together. Okay, so we're going to be dealing with ands and ors because our two inequalities are going to be either separated by an and or an or statement. So first of all, with an and statement, this consists of all numbers that satisfy both of the simple inequalities. Okay, in other words, we're talking about the intersection of the solution sets. Now, you got to be careful with this because using and in a mathematical sense is not like using and in everyday English language. For example, if I were to say I had bacon and eggs for breakfast, you would assume that I had all the bacon and all the eggs. I had everything that was on my plate. But in math, we're not talking about everything that's in both of the simple inequalities. In a mathematical sense, we're talking about what's shared, okay? So in an and statement, we're looking for what the two simple inequalities share as part of the solution. And here's a Venn diagram that kind of shows that. If we had our first inequality represented by the A circle and our second inequality represented by the B circle, if each circle was a representation of all the solutions for our two inequalities, the part that's shared would be the intersection, and that is what we would consider as part of our solution for the compound inequality. And this will make more sense here as we get into doing some examples. Now, the other thing that can separate two of these inequality statements is an or statement. This consists of all numbers that satisfy at least one of the simple inequalities. In other words, we are talking about the union of solution sets. So here we are talking about everything. We take all the solutions from one inequality and we put it with all the solutions of the other inequality, and all of that together would be our solution for the compound inequality. And here we have a Venn diagram again showing the solutions for inequality A, the solutions for inequality B, and we would include everything. Whether it's shared or not, everything would be included in your solution. So let's do a few examples to kind of get this under our belt. So here we're not solving anything, we're just presented with some solutions, and we're going to talk about how we're going to graph these. So let's say we had our solution being x is greater than 2 and x is less than or equal to 5. Well, let's start off by sketching what x is greater than 2 looks like. Our point of interest is 2. It would be an open dot because we're not including it. And since everything's greater than, we would shade everything to the right. Now for x is less than or equal to 5, we would start at 5, it would be included, and since x is less than, we're going to go to the left. What we're looking for, because this is an and statement, is we are looking for everything that is included in both, okay? So everything that is shared in between the two. So really, if you sketch it this way, you can look and see where we have one line on top of the other, and that's between 2 and 5. So we're not including 2 still as part of our final solution because it's not included in one of them, and we're going to go up to 5, and then we'll fill the dot at 5. And that would be our solution set for the compound inequality. The way we can notate this is, well, we could combine it, and we can do that looking at the number line, okay? And statements you can combine into one statement if you so choose. So we could say that 2 is less than x, which is less than or equal to 5. And this makes sense, right? Because all of our values for x are going to be between 2 and 5. And that's represented here in our number line. And we put the equals to part onto the 5 because that part's included. Interval notation, our lower bound is 2 and it's not included. Our upper bound is 5 and it is included. So that one gets a bracket. All right, let's move on to the next example. Now we have an or statement. We want to express x is greater than or equal to 4, or I should say just x is greater than 4, or x is less than negative 1. So let's start with x is greater than 4. Well, we have 4, open dot because it's not included, and we're going to the right. Then we have x is less than negative 1, also not included, and going to the left because it's less than. Well, since this is an or statement, we're going to include everything between both of our simple inequalities. So we're going to have an open dot at negative 1, and we're going to go to the left, and we're going to have an open dot at 4 and go to the right. Now, the way we express this in set notation is the set of all x such that x is greater than 4 or x is less than negative 1. There's really no other way we can express that because we're talking about two separate sets. So you'll notice I basically pulled what our solution would be verbatim down into our set notation. And then finally in interval notation, our lowest bound, we're coming from negative infinity, and we're going to negative 1. And then we have another part that we have to include. So remember, we talked about or statements being a union. This is where this u comes from in interval notation. And we have 4 to infinity. And that's how we express the answer in interval notation. All right, let's move on to a couple more examples because I kind of want to give you an idea of what different types of solutions may look like. So let's express x is less than 3 and x is less than 5 on a number line. Well, this is an and statement, so we're going to be looking for what's shared. Let's start with x is less than 3. Well, we're not including 3, so it's an open dot, and it's less than, so we're going to the left. And then for x is less than 5, 5 is not included, and we're going to the left. So what's shared? Well, everything that's shared is everything that's less than 3. And we're not including 3 because in the red one, 3 is not included. So open dot still at 3, and we go to the left. You'll notice that the solution looks very much like what we had with our red inequality. So you can use that to kind of help you figure out what the set notation solution is. But really, if you just look at the number line for our final solution, you'll see the open dot at 3, which means it's just going to be a greater than or less than, and the shading to the left tells us it's less than. Then in interval notation, we are going to start with our lower bound, negative infinity, and we're going to our upper bound, which is 3. So you'll notice that in this and statement, we did not necessarily end up with the compound inequality as part of our set solution because it wasn't necessary. All of our solutions just happened to be what was included in x is less than 3. Okay, let's do another OR. In this example, we want to express x is greater than or equal to 4 or x is greater than or equal to 0 on a number line in set notation and in interval notation. So just what we've been doing. So let's start with x is greater than or equal to 4. Greater than or equal to means that we're going to include 4. And since it's greater than, we're going to the right. X is greater than or equal to 0. Since it's equal to 0, we're going to include it. And since it's greater than, we're also going to the right with this one. Okay? Now, let's look at what the final solution is going to be. Since this is an OR statement, we're going to include everything whether it's shared or not. Okay? So, you'll notice that everything on the red line is already covered in the green line. So our solution is pretty much going to end up being what we have along our green line. And that green line in set notation is all x such that x is greater than or equal to 0. And then in interval notation, we're starting with our lower bound, which is 0, and we're including the 0, and we're going to infinity. All right, our next example. Let's express x is less than 2 and x is greater than 6 on a number line in set notation and interval notation. So x is less than 2. Well, we know we're not going to include 2, and it's less than, so we're going to the left. X is greater than 6. We're not including the 6. It's greater than, so we're going to the right. Now, this is an AND statement. So since we have an AND statement, we want to do what's shared. But what's shared between these two? Well, the answer is nothing is shared. So when we come down to our number line to graph our solution, we're just going to leave our number line alone because there's nothing to graph since there's nothing that's shared. In interval notation, we would notate this as just saying no solutions. And then in set notation, there's two ways that we can notate this. You can either put the set with nothing in it, that's notated by your curly braces, or you can write a 0 with a slash through it. Both of these represent what we call the empty set. It's an empty set because there's nothing in it, because there are no solutions to put in it. All right, now let's move on to example 8. Express x is less than 3 or x is greater than 1 on a number line in set notation and interval notation. So more of the same. X is less than 3. Well, we've got 3 not being included. And since it's less than, we're going to the left. Or x is greater than 1. Well, we're not including the 1, and we're going to the right. Well, since this is an OR statement, we're including everything, whether it's shared or not. Well, that takes us across the whole number line, right? And beyond. So the way you would handle this on a number line is that you would just shade in the entire number line. And what does this mean in terms of what our solution would be? Well, this tells us that we have all solutions, or infinitely many solutions. So in interval notation, we have negative infinity to infinity. And in set notation, you can put in your curly braces the fancy R, which indicates all real numbers. And this is how we notate all solutions. Everything is a solution. That is a real number, that is. Okay, so that is how we go about expressing answers for compound inequalities. Now let's put everything together and let's solve compound inequalities. Now that we know how to express a solution, we're just going to add that last little bit of solving a compound inequality. Now, to solve a compound inequality, written as a single statement, you can either separate the inequality into two individual statements with and then solve as you would for a simple inequality, or you can leave the inequality as a single statement and isolate the variable by using inverse operations on both sides of the inequalities. That sounds like a lot, but I'm going to go through how to do both ways. And I only really recommend solving the inequality as a single statement if you have a variable in the middle. It gets a little messier when you have variables on the outsides. Okay? So in this first example, we have a variable in the middle, but not on the outsides. Okay? This is a compound inequality statement, and when you see a statement like this, this is always going to be an and statement. So let's do it the traditional way first. Let's split it up into two simple inequalities. So you got negative 11 is less than negative 3x minus 8, and you have negative 3x minus 8 is less than or equal to negative 2. Well, we can solve these individually. We can add 8 to each side and get negative 3 is less than negative 3x, and then divide by negative 3. Remember, dividing by a negative number means you're going to have to flip the inequality. So you get x is greater than, or I should say 1 is greater than x. Let's go over to the other one. We'll add 8 to both sides, and when you do so, you're going to get 6 on the right-hand side. And then divide by negative 3. Again, you're going to have to flip the inequality, and that's going to give us negative 2. So x is greater than or equal to negative 2. And the and statement comes along for the ride. Okay, so we have a solution now. Before we get to graphing the solution, let's see what it would look like if we were to do this all as one statement. So if we were to do this all as one statement, you can add 8 to all three portions of this inequality. And when you do so, you get negative 3 is less than negative 3x, which is less than or equal to 6. And then you divide all three parts by negative 3. And remember, when you do that, you're going to have to flip your inequality signs both times, okay? So you get 1 is less than x, or I should say, because we want to flip that inequality, 1 is greater than x, which is greater than or equal to negative 2. Okay? Now, if we were to write this in set notation, we would flip everything and lead with our negative 2. Negative 2 is less than or equal to x, which is less than 1. We lead with our negative 2 because we often read our negative numbers to the left and our positive numbers to the right, or our smaller numbers to the left and our bigger numbers to the right. Okay, so that's our set notation. Let's look at the line. And you'll notice I did not provide a line this time because I want to show you how you can sketch it on your own. So let's sketch a line, and all we need to put on it is our 2 points of interest, negative 2 and 1. Okay, so for our first statement, we have 1 is greater than x. So we're not including 1, and 1 is greater than x, which means we're going to the left, okay, because x is less than 1. Now, for the other one, we have negative 2. We are including it. And x is greater than or equal to negative 2, so since it's greater than, we're shading to the right. So now, on your number line that you would be presented with negative 2 and 1, your solution would be what's shared because this is an and statement. So we have everything from negative 2, including negative 2, up to 1, not including 1. And on interval notation, that would be negative 2 included with a bracket to 1 not included with the parentheses. Okay, so that was a little bit of work. We had to solve the inequality first. I showed you two ways to do it on this one, and then we were able to express our solutions. So let's do a few more to get a little bit of practice. Well, this one, we have variables in all three spots and on the outside. So this one's going to be a little bit more complicated to do as one statement. So it's my preference, and I tend to always do this anyway, is just split it up. If I always split it up, then I don't have to worry about when can I split it up, when is it harder to split it up. If I just split it up every time, then I know I'm always going to be okay. So I'm just going to split this into our two statements. The middle portion gets repeated twice. It's part of both of our two inequalities. Okay, so let's solve this first one. Well, let's start by subtracting x from each side. And when we do that, we get x minus 8 on the right-hand side. Then we add 8 to each side. We get 18 is less than x. Now let's move to the other one. Let's start off by subtracting 2x from each side. And when we do, we get 8 plus x on the right-hand side. And then if we add 8 to each side, or I should say subtract 8 from each side, we get negative 16 is less than or equal to x. And you have your and statement in between. Well, let's see how this looks graphed before we get into writing any solutions, because that's going to give us a lot of information like it has so far. Our points of interest are negative 16 and 18. Okay, let's graph the first one. X is less than, or x is greater than 18, 18 is less than x. If x is greater than 18, then we know we're not including x, or we're not including 18. And if it's greater than 18, then we're going to the right. Well, x is greater than or equal to negative 16. So we include negative 16, and we also go to the right. Well, if we're including everything that is shared, then on our solution number line, which I'm going to draw down here, we've got negative 16 and we've got 18. Well, if everything that's shared, we're doing basically what we have in red here, and that would be our solution. That helps us when we get into doing set notation, because we can see on our number line that we have x such that x is greater than 18. That would be our solution in set notation. And then in our interval, it would be all points from 18 to infinity, not including 18. All right, let's move on to the next example. Let's solve this statement, which is an OR statement. 7x minus 10 is less than or equal to negative 59, or 3 minus 2x is less than negative 15. All right, let's start by solving the left-hand inequality. Let's add 10 to each side. And when we do, we get 7x is less than or equal to negative 49. Divide each side by 7. We get x is less than or equal to negative 7. And remember, we divided by a positive number here, so the sign is okay. On the other inequality, let's subtract 3 from each side. That gives us negative 2x is less than negative 18. And divide each side by negative 2. Now we have to flip the sign, and we get x is greater than 9. All right, so now let's graph our inequality. And let's graph each part first. So negative 7 and 9 are points of interest. So for the first one, x is less than or equal to negative 7. We have negative 7 included, and x is less than or equal to it, so since it's less than, we're going to the left. For the other one, x is greater than 9, we don't include 9, and it's greater than, so we go to the right. Well, since this is an OR statement, because remember, this OR comes on down with it, we can graph on our solution number line. There's negative 7, there's 9. We can graph everything that's included. So everything that's goes with this inequality and everything that goes with the other inequality. And that whole thing would be our solution. We're just omitting everything between -7 and 9, and we're omitting 9 itself. So in set notation, because this is an OR statement and we've got two different sections, there's no other way to write it other than x is less than or equal to -7 or x is greater than 9. In interval notation, we're coming from -infinity and we're going to -7, and we include the -7, and we're going to union that with 9 to infinity. All right, let's move on to this next example. We are going to solve 5 minus 7x is greater than or equal to 12, or 3x minus 2 is less than 7. Okay, so the first thing we want to do with this first one is subtract 5 from each side. So we get -7x is greater than or equal to 7. So x is greater than or, well, actually, we're dividing by a negative number. So let's make sure we flip the sign. So let me go ahead and erase this. See, it's a good reminder to make sure you flip the sign. It's very easy to forget to do that. All right, we flip the sign because we divide by a negative, so we have x is less than or equal to -1. Also, a good thing to remember is not to move too quickly when you're doing these things, because it is easy to forget the little things. All right, let's move on to the other one. We're going to add 2 to each side, so we get 3x is less than, adding 2 to 7 gives us 9. And then x is less than 3 when we divide each side by 3. And the OR comes along. Okay, so now let's see what we have individually before we graph our final solution. So we have our points of interest being -1 and 3. Our first equation is, or I should say inequality, is x is less than or equal to -1. So we are including the -1, and it's less than or equal to, so we are going to the left. X is less than 3. We're not including 3, but here we're also going to the left. And let's do this one in green. Okay, so once we have that, we're looking at this being an OR statement. And since this is an OR statement, we want to do everything between the two. So when we do everything between the two, we're going to end up with an open dot at 3, and we're going to the left. So we're shading everything in, going to the left. In set notation, this is going to be the set for all x such that x is less than 3. And in interval notation, we're covering everything from -infinity to 3, not including 3, so we use a parentheses. Okay, let's move on to example 13. So we want to solve -4 minus 4x is greater than 3x minus 4, and 6x minus 6 is greater than or equal to 8 minus x. So when we do this one, we are going to, first of all, solve them. So let's solve first by adding 4x to each side of this first one. So that gives us -4 is greater than or equal to, or I should say just greater than 7x minus 4. If you add 4 to both sides, you get 0 is greater than 7x. So therefore, 0 is greater than x, because we divide each side by 7. On the other one, let's add x to each side. Let's move this over. We get 7x minus 6 is greater than or equal to 8. Let's add 6 to both sides. So you get 7x is greater than or equal to 14. And then finally, x is greater than or equal to 2 when we divide each side by 7. And our n comes along for the ride. So let's graph each one individually. So you would have our points of interest being 0 and 2. For the first one, x is greater than, or I should say x is less than 0. So we have an open dot at 0, and x is less than, so we go to the left. And for the other one, x is greater than or equal to 2. We have a closed dot, and since we're greater than, we're going to the right. And since this is an and statement, we don't have anything included. So your number line, as it's presented, would just stay blank with nothing plotted on it because there's nothing shared between these two solutions. When there's nothing shared, that means there's no solutions, simply put in interval notation. And remember, there's two ways that we can represent this in set notation. You can either use the curly braces with nothing in it, or you can do a 0 with a slash, both of these representing the empty set. Okay, now let's move down to example 14. We're going to solve this set of inequalities. We're going to solve x plus 5 is greater than or equal to 2, or x plus 4 is less than 7. Well, these are pretty simple to solve. We subtract 5 from each side, we get x is greater than or equal to negative 3, or when we subtract 4 from each side, x is less than 3. Okay, let's graph these individually. Our points of interest being negative 3 and 3. And let's start with the left-hand one. We are including negative 3, and it's greater than, so we're going to the right. We are not including 3, and it's less than, so we're going to the left. And since this is an or statement, we're doing everything along the line. So if you were presented with a number line, your solution would simply be everything that is along that line. So you would shade the whole line like we've done before. In interval notation, since we're including everything, it would be negative infinity to infinity. And in set notation, we're including the set of all real numbers. This is all solutions. Okay, so this kind of wraps up this portion of the notes for this section before we go on to one final example. This kind of shows you how to work with the inequalities, how to express the solutions, how to solve for them, how to handle and statements, how to handle or statements. Let's wrap this section up by doing one final example where we look at a real-world use for compound inequalities. So here's an example where we have a radio station in a town called Winchester, and it sends out signals for a radius of 100 miles. Winchester would be located here at this dot. Okay, so this would be Winchester. The Thiesville radio station sends out signals for a radius of 60 miles. So Thiesville would be up here. And you're driving from Winchester to Thiesville, so we're going this way. The distance that we're traveling from Winchester to Thiesville is 200 miles. So what we want to do is write an inequality that represents our location while we can listen to one of the two radio stations on our car radio. Okay, so since the signal only goes out 100 miles from Winchester, we're going to hit a point where we lose the signal. And we have dead air until we get close enough to Thiesville to where we're within 60 miles and picking up the signal from Thiesville, and we're able to listen to the radio again. Okay, so we want to represent, using a compound inequality, what is the times in that 200-mile trip that we can listen to the radio. So let's define a variable, d. Let's let d be the distance that we have traveled from Winchester. So this is the distance traveled from Winchester, because Winchester is our starting place. Okay? So we know that the Winchester station can be heard up to 100 miles away. So how can we represent the distances d when we are listening to Winchester? Okay, listening to W. Well, at 0, distance 0 traveled, we can listen to Winchester. We can hear it from 0 to 10, all the way up to 25, up to 30, 40, 50, all the way up to 100 miles out. So for every distance that's less than 100 miles away, we can listen to Winchester. And let's go ahead and say we are including that 100 miles out, and then we lose our signal completely. So we would include all distances that are less than or equal to 100. All right, let's talk about the distances when we're listening to the Thiesville station. Well, we know if we've traveled 200 miles that we can hear the Thiesville station. And we can hear it at 190 miles away from Winchester. We can hear it from 180 and 170. So we can hear it from 200 miles away minus the 60 miles until we get to Thiesville. And so it would be for every distance that is greater than or equal to the 200 minus 60. Okay? Because 200 minus 60 would be the point in which we hear it, and then everything beyond that, we can hear it. So we can go ahead and simplify that to be for every distance greater than or equal to 140. So it's at 140 miles out from Winchester that we hit the first moment that we can listen to the Thiesville station. Now, think of this distance that we traveled, this line. Think of this as our number line. So we have a portion along here that we could hear it, and we have a portion along here that we could hear it. So since we have two parts that we can hear it, and we want to include both sections, then we are going to use an or statement, because we can listen to the radio here, closer to Winchester, or we can listen to it here, closer to Thiesville. And so our solution set, which is what they ask us for, would be the set of all distances such that the distance is less than or equal to 100, or the distance is greater than or equal to 140. And that kind of gives you an idea of how we can use compound inequalities and apply it to some real-world sort of problem. So this ends the section 2 notes. As we move on to section 3, the next section will be on linear programming.